Awesome. Greetings, healthcare colleagues. My name is Kevin Kotchek. I'm the founder CEO of Chemical Q Device. Today is June 1st, 2023, discussion 85. So this is about quantum computing leadership. So as it relates to future medical innovations, it'll start off kind of general, as in what you'd search for, Google search, those types of things. So the first thing is University of Chicago is very active in quantum and that surrounding area as well. So they have a practical scale, organization or portion of their university is dedicated to EPIC, EPIQC. They've received NSF grants for all of this. Fermilab, Argonne lab, these are national labs. They also are working on internet, so quantum internet. Also Fermilab MRI analysis with this as well. So quantum sensing, quantum computing. You have Chicago Quantum Exchange, which Barack Obama, basically viewed kind of like the students going through the routines there. Also, Harvard University Diamond Sensors silicon vacancies. They don't just do nitrogen vacancy. This is for memory, for internet. Prospectively, this could be for quantum computers, other purposes as well. They have an AWS partnership for internet, advancing quantum internet. Also the Harvard Google QML paper, they do a lot of stuff with MIT as well. It's interesting, if you look at a lot of the leaders, for quantum computing, you'll find Seth Lloyd graduated from Harvard, and now he's, doing very well at MIT. University of Maryland, so this is also East Coast here. They have a NIST partnership. In addition, they have IonQ National Lab, that affiliation too with NSF grants. Terra Quantum AG is overseas, but they do a lot of stuff with simulators versus real hardware. So you'd be surprised how many qubits you can get up to, and it's still faster to run on a quantum simulator because of initialization, these types of things. They also do quantum as service and quantum algorithms as well. So we'll be talking about these in twos. QuEra Computing, which is that middle one that I'm featuring, is basically they do neutral atom computing. They're featured on AWS Briquette, so you can go rent time using their quantum computer. And their pricing isn't fully understood by me, but basically it's equivalent to one of the IonQ quantum computers. So that may be a function of popularity with it. So it's definitely one of the top as far as cost to get on. NVIDIA is by far, one of the leaders with this. It's split up into two things. You have QQuantum, which is quantum simulators, which is doing quantum mechanics on CPUs or GPUs or both. And then you have CODA. So CODA is not CUDA. CODA is QODA, and this is in specific real quantum computers, also in tandem with CPUs and or GPUs as well. They have this service called DGX Quantum that's to help out with error in the quantum computers, a GPU. Is there a question? And then yeah, so we'll talk about these two. So software development kits, especially with QQuantum. So if you're looking to use NVIDIA right away, it would definitely be that QQuantum, which is basically means CUDA, which is their GPU plus quantum. So the abbreviations and even the NVIDIA reps, if you watch a bunch of these videos online, admit that, it's getting there. We'll come up with something. University of Southern California. So they have QIST. QIST. They also do a lot with quantum annealing and their association with the IARPA for practical advantages. So as you may know, you can get quantum advantage with quantum annealing for specific optimization problems. And that's primarily what they're after is that kind of quantum annealing. Now, Stanford University has a lot in terms of courses and these types of things. They have a thing called QFarm, which is engineering fundamentals, architectures, and machines, and organizations for grads, undergrads. The one that kind of sticks out, I guess, for universities this last on the West Coast here is UCB, which is University of California, Berkeley, and that has graduates such as Scott Aronson, John Martinez, who led quantum supremacy back in 2019 with Google. And they have student groups, undergraduate research opportunities in quantum, quantum machine learning, particle reconstruction. Berkeley lab is associated with the, or it's in the same city, basically. It's by the university. Quantum system accelerator and advanced quantum test bed. So with that, I'm interested because, obviously 6 of these 9 are universities, and a lot of the innovation starts there, and they turn into partnerships with other, startups, and, who knows, like the next INQs, those types of things that don't have like a big parent company like, say, Quantinuum does. So were there any questions or comments? So we could start off basically with University of Chicago and Harvard University. So these are, well, I guess University of Chicago might be more Midwest, but more towards the East Coast, with quantum computing. So yeah, any questions with that? And then, a lot of this is heading towards medical. So it's going to be technical, right? Because we don't have full packages for certain things. Like there's not an AWS specific package for medical image analysis that you could just click on and insert your data set, those types of things. So there's not a ton of mainstream news besides like IBM and Cleveland Clinic and Mount Sinai Hospital, NYU Langone, but they've definitely, it's definitely out there that people and organizations are supporting quantum computing. So, I touched on University of Chicago just a little bit, but there's other people that join the discussion too. And that's the thing, is like, it's a huge area for quantum innovation, right? So you have president going in person to see students learn on quantum technologies. And, there's that partnership too between Fermilab and Argonne is really big, because they were the first to transmit both quantum and classical data all at the same time. So when you're thinking about these and basically how it relates to patient data, just imagine, you could do something better, on a quantum internet than you could before, if it's speed or if it's the type of data. But an issue with quantum memory is to store quantum data is that it doesn't last as long as we want it to. And so that's a big initiative too. Now with Harvard University, you'll find a lot of these kind of like collaborations with Google, or MIT, and it's to support very specific things that can lead to other breakthroughs in the industry. And I've featured this before, such as quantum sensing. So quantum sensing has been used to improve performance of quantum computer with a quantum mechanical effect with sensing. So noise was no longer the biggest issue with that. Yeah, go ahead, Mark.
What I'm most interested in, and I'm just kind of listening in on this. I kind of work with a lot of companies in medical imaging on the front end of development, so understanding user needs and where that meets emerging technologies. So I'm very interested in this topic, particularly when things are moving towards kind of where they move out of research labs and into commercialization. So that's where I work. So I'm just listening in, looking for hands. I didn't mean to interrupt. I think for some reason I wasn't on mute,
yeah, I mean,
that's what I'm here for. Yeah.
So I'm working on an application. It's medical image analysis, and a lot of it is just it's non-medical appearingly. Like I watch a lot of the authors' videos, and I'll read supplementary material, because in quantum mechanics or quantum computing, you don't always have to use like the full circuit. Like there's specific things that are going on behind the scenes. So say, for instance, you want to separate two things, and the quantum method is a lot better at doing that. And you only need to use a specific technique as opposed to like a mainstream technique. So you find these things out by following the, Penny Lane and these other organizations that post models and updates and these types of things. But, the breakthroughs have come through, in my opinion, because I have some things lined up after my June update here, is that the breakthroughs have come through for very specific uses of quantum code, like what you do and what you don't do. And it'll be hybrid, right? So everything's hybrid now, but we're stuck in linear circuits right now for quantum computing. So we'll go into quantum neural nets, which will act more like a deep learner, right? Deep learning residual network, stuff like that. And the roles will start changing as the quantum computers and quantum simulators get better. And then instead of doing cats and dogs or ants and bees, now you're doing, real life patient images. But it's the same principle, right? Like it's learning off of just like curves and the actual images themselves, like a convolutional neural net. So where we are right now with all of this stuff as it applies to medical is, as I mentioned before, you'll have a linear circuit, and they're getting bigger, right? Because the hardware is getting bigger and the simulators are getting bigger. And there's certain functionalities such as entanglement, and you'll do a certain quantum gate, which is a matrix, and that'll do, it's called superpositioning. And then you also have interference. Those are the three main things. So entanglement, interference, and superpositioning. So I would start, and this is very common in this discussion, is if you want to get into this, start with IBM Qiskit, do penny lane demos. I have a fair amount of material up too. It's all open source because I'm kind of moving on to next kind of stuff. And you want to understand what a gate is, a circuit is, that a circuit contains a quantum algorithm. So when I use these terms, and where it'll be moving into, it'll be a while before we have an FDA approved quantum hybrid algorithm, in my opinion. But say, for instance, you're dealing with quantum simulators, which are noise free, versus quantum computers. So I hope that answered some questions. Was there any other questions either from Mark or anybody else? So this is definitely an emerging field that we're dealing with. And, you'll see stuff in literature. I want to address the most general needs here, right? So if that's just getting started, programming a circuit, running it on Qiskit, doing a model, in my opinion, it's all about applications. So penny lane models tend to be the one that their end result is more aligning with what's currently going on in the world. So try to fix it, try to make it better, because you can modify code and you can modify algorithms too. So I hope that answers your question, Mark. And then, so we had some other people pop on here. So basically, we talked a little bit about University of Chicago and Harvard. The next two are University of Maryland and Terra Quantum AG. So University of Maryland has a partnership with IonQ. Now, IonQ is probably the one of the, if not the most, leading in terms of quantum computing hardware with it's called ion trap technology. And a lot of these, like if you look on Google Maps and do a street view, you can go up to, IonQ's, their business is bigger than most of the other quantum computing hardware manufacturers. So it's got, a good amount of funding. They say manufacturing facility early next year. And again, so tying this into medical is, what will be that threshold of, I don't believe quantum simulators should be much of a problem getting approved. They run on CPUs and GPUs. I could be wrong, but quantum computers have a significant amount of noise even today, like the best ones, and it'll take time. So the other one is Terra Quantum AG, and they did a paper just that they compared quantum simulators to quantum computers, and there's a threshold. So they said at 30 qubits or less, you want to run on a quantum simulator, even though by specs, quantum computers should be faster at that point. There's slowness, there's latency in quantum computers, whereas a quantum simulator with more established hardware, there's not. And like I said, they offer quantum as a service and quantum algorithms too. So, so anybody else? So Anand or Mary, I see you joined as well. So feel free to come on, or you can unmute your mic. And then the chat also is open here too. So feel free to post anything in there. And it's just going to take some time, right, before we see the breakthroughs in medical. But I mean, as long as you just keep working on it and understand it's, a real quantum computer with patient data because of error, sounds like it's going to take a while. So Leiden or Avik, any other questions or comments with this as it relates to quantum computing or medical? And then if not, I see Lorraine. So Lorraine was a speaker on this discussion earlier before. So Lorraine or Renato or Ella Riza, any other comments? Kind of, your quantum journey, where you are now, or any questions as this relates to medical? And again, so the chat is open. Yeah, go ahead.
Excuse me. So I have a fundamental question. Maybe it will be very simple for you or others. So in medical approaches or any advances there, you want to use any approaches for quantum computing for, I do not know, any physical instruments such as MRI, or any development, any quantum development, any software based on quantum computing? Or could you please explain a little more?
Yeah. So basically, you could split things up between quantum sensing and quantum computing. Now, lasers and MRIs are technically considered quantum sensors because some of the processes, or at least one, abides by the principles of quantum mechanics. So that's quantum sensing. So the buzz these days in the past couple of years has been about quantum computing because, the simulators are getting better and the hardware is getting better. So say, for instance, like if you have something like medical image analysis, you're dealing with a classical image, and then you're basically turning it into quantum data, and then it gets turned back into classical data in order to get a quantum advantage. So the biggest quantum advantage comes if you have quantum data, but that needs quantum memory, and we don't have that very well today. So in the future, if you have images that are based on quantum data that go straight into a quantum circuit, and then at the end it gets turned back into classical, for like a bit. So that's basically it. I mean, it's like with quantum computing, it's for very specific purposes, and you have to understand what gates are doing what things, what blocks of code. So in the beginning of a quantum circuit or algorithm, you'll have, it's called a embedding layer. So that takes the classical data, converts it into quantum data, and then you'll have this variational layer, which does manipulations of that quantum data, and then you'll convert it back to classical data as well. And the big thing with all of this is computational cost. So if I go to, install a bunch of entangling, they're called CX or C0 gates, it makes things slower. But in theory, it should make things higher performance. And it's very specific to the application. So with mine, I only need certain aspects of, a circuit to do the specific thing, right? So you don't want to always run a full quantum circuit, or like say like a small or a medium quantum circuit, just thinking that that'll always work. And in literature, you find that you'll find a lot of different variations to the quantum circuit there. So yeah, that's the big push, is quantum computing now. They used to call quantum computing, you would do physics or quantum mechanics on a piece of paper, and your professor would ask, what are you doing? And you'd say, I'm doing quantum computing, because we didn't have the hardware. So that's the big push right now. It's between photonics or gate-based superconducting qubit or ion trap, neutral atom, silicon spin qubits, these types of things. They all do things a little bit different as far as what it took to compute a quantum algorithm. So and some like ion trap and gate-based superconducting qubit are ahead with actually doing that quantum algorithm more predictably than others. And did that answer your question?
Yeah, thank you so much. I have another question related to the quantum data. For example, this data can be considered also for example, interaction between neurons in our brain, or anything related to this one, or?
Yeah, so quantum data is typically associated with having a quantum sensor, and then you're getting quantum data from that. And that whole process, say if you want to do that for I'm going to start with the images because I just know it a little bit better, that now your MRI is using a specific quantum sensor at this point, and it's not turning it into bits like zeros and ones. It's turning it into like superpositions of zeros and ones, like complex. It's called higher dimensional, like that you could store a lot more information in a qubit, a quantum bit, than you can a bit. So that's the advantage there. Is you say for images, you can separate the images a lot better because you have a quantum bit, and then you can kind of direct traffic into how you want to separate categories better. So yeah, quantum data. Okay. So there's 4 types. There's CQ, CC, QC, or QQ as variations of quantum data, or as variations of algorithms or data, varying either the classical part or the quantum part. So the most likely scenario you see these days is a CQ. So we have a classical data, like on an image, it's just 0, 1 in storage, and then you have a quantum algorithm that's processing it. So there's a QQ, which would be quantum data, quantum algorithms. And that quantum data, like I said, is if it's like a natural example from nature, I think it needs to be obtained using a quantum sensor. That's typically the route.
Yeah, thank you so much. Can I ask you another question?
Yeah, go ahead.
Okay. So related to image, for example, from MRI machines. So from classical images, the pixel range, I mean, the binary images will be 0 or 1. Well, how about the quantum images from the?
Yeah, so it's 0, 1, or anywhere in between. So that phenomenon with a quantum bit, it's represented by something called a block sphere. Is it could be 0, it can be superpositioned. So 0, 1, or anywhere in between. And I believe you can break it up as how you see it. But yeah,
So,
it's complex numbers, and then it's a lot more information. So that's the advantage, is that you're gaining a lot more with that quantum bit than you would conventionally with a classical bit.
okay, good. So you believe that if we consider the superposition of quantum states for observe, so it will help to observe more details from, for example, our brain or some things from our images?
Yeah, so you take steps, right? Like you just don't have like this fully functional, we understand human consciousness based off of EEGs and MRIs. You just don't have that right away. So like I said, it starts with data acquisition, right? Like, so you're getting the raw data via, quantum sensor or classical, and then you're converting that into an actual, image, right? So it's like a quantum database. And I will say this it's important fact is that in all these things, say for instance, if you have like a typical quantum circuit in IBM's thing, it's called Qiskit. The time to process or basically the RAM requirements is 2 to the n. So that means that as you insert more gates and the complexity of it, the GPU and the CPU get really bogged down if you do it that specific way. But there's other ways to do it, and it's 2 times n. But yeah, a lot of times you're looking at simple mathematical expressions as far as like, should we use this for that? And then say, for instance, a different method called tensor network quantum simulator doesn't do, say, entanglement as much, and it is just it's more limited, but it can do lots more qubits. So you can do, instead of like I was 20 or 30 qubits, instead you can do over 100 or sometimes into the thousands, but it's limited, right? So a lot of times there's no one size fits all with quantum. You really have to read the papers, do the models, improve the models. If you can code, like come up with your own portions of code to improve chunks of it. And it's just like there'll be a new paper out, and then you'll say, oh, okay, I want to apply this to this previous model, those types of things to the quantum data. So we can come back to this, but there was a question. So I'd like to learn more about quantum computing for genomics. So genomics is a biopolymer, right? So biopolymers like RNA, DNA is what we're talking about here. They're huge molecules, and quantum can't quite do that either, And again, it comes down to specific methods, but we're talking about, small molecules for, the closest thing I could think is like drug discovery. We can do that kind of stuff with a technique called quantum annealing, but it's really, it's okay. There's at least 10 organizations or companies that do drug discovery. Okay, so some of them do RNA, I think some do DNA. And as far as I know, they're all making high approximations to molecules or biopolymer, really long, molecules. And then they're using a technique called quantum annealing, which is only for optimization. But apparently they're getting results. It's just we don't have like broad quantum advantage where it's just like, oh yeah, this will work in this specific case, and also that is a lot of times it's a very specific thing. Like even in medical image analysis, it's not necessarily like following the rule, like the general rules, but then you read these papers and then you're like, oh, okay, I can use my circuit like this. And feel free, Mary, if you have any other questions. Quantum annealing, yeah. So quantum annealing is basically a company called D-Wave. So D-Wave was formed around the turn of the century. So that was around like 1999, 2000. And then so they've been working hard at this technology, and the qubits, so the qubits are higher than some of the ion trap and gate-based superconducting qubits, but it's limited. So it's only for optimizing things. So if you have like, and it's more complex than this, but like, 10 boxes and 11 screwdrivers, what is the best combination for whatever task you're trying to solve, kind of thing. So yeah, D-Wave has a bunch of applications out there, and there's layers, right? So you did something on quantum, and then how much better is it than classical? And then so you keep stepping up. So, more and more quantum advantage based on your technique or the hardware. So yeah, so that Fujitsu does some of this too, but the one that's more accessible in the US is definitely D-Wave. And they do some other stuff such as feature extraction, but they've worked with like GE, like these really big companies, either aerospace companies, not for flying at this point, but just some other issue that they had. They had out here, Port of Los Angeles, kind of optimizing not the boats, but like the cargo shipping containers. So D-Wave had an application with that. So there's a fair number of people out there that are happy with their D-Wave optimization results. You can say you use quantum computing at elevated qubits. I'll probably be more towards like this tensor network GPU simulator kind of stuff, because it seems like it's going to suit my needs. So yeah, just be aware of that. There's no one-stop shop between IBM and INQ, because there's inherent differences in the technology. So yes, so that's interesting. So Mary said she went to a D-Wave Vancouver workshop about their organization and projects. And they're kind of like one of those industry leaders, or like a pioneer. They actually started with gate-based superconducting qubits, but that was too hard. So they've been doing, they actually had they sold their first quantum computer to Lockheed Martin. It was $10 million. I can't remember the year, but it was not too long ago, maybe in the 2000s, late 2000s, something like that. Yeah, so their standard, as far as I last checked, and feel free if you want to come on, Mary, that's fine. As far as I know, the last time I checked, they were at about 5,000 qubits, but it's not like apples to apples with basically all the other mainstream quantum computing technologies. And then so okay, so we have another question here. So related to quantum advantage, there's a technology. Yeah. which is applicable. Okay, so NISQ or noisy intermediate scale quantum was coined, I think, by John Preskill of Caltech. And basically NISQ applies to all quantum computers today. All quantum computers, as far as we know, are in the noisy intermediate scale. And then the next ones are like partially error corrected, or, you know, there's stages to get to full error corrections. So, you know, that's all quantum computing hardware for sure. And if you want to get started on a project, there's going to be a lot of noise, right? And your whatever analyses are just going to not be great, but you say you worked on it. So you could go onto IBM Qiskit and you could run on a 7-qubit IBM Nairobi, which I've run on a lot. And at low, like this low circuit gates and circuit depth and all these types of things, you won't get too much error. But if you start doing anything with the algorithm or make the algorithm bigger, you get even more error, because there's error that gets introduced at every quantum gate. So if you imagine hundreds or thousands of quantum gates, then, you know, you really have that error going on. So faultiness. But yeah, that's the term, that's the stage that quantum computers are in, is we're in the NISQ era for ion trap or gate-based superconducting Q2. Any other questions? Anybody that we haven't heard from here? So appreciate all the comments here. So Anand or Renato, any kind of comments or questions? So we made it through all of these as far as ending at UC Berkeley. And that was kind of like the objective. And going into medical, I mean, it's part regulatory, because a lot of people don't know about quantum simulators as much as quantum computers, but they're basically error-free. They're slow, especially on like a single CPU that's not very good. But NVIDIA in specific has these better GPUs and multi-GPUs that even though you're kind of bound by some of these limitations in runtime, that it's looking like it's going to overcome that, especially in the near term. And if you were on a couple weeks ago, I shared a couple of links. There's Tom's Hardware, and then another, I think it's AZO, is some other market report. And they said in the near term, you know, expect to either use, you know, quantum simulators or single GPU quantum simulators, because the error is just too high. I was just running 3,500 images, and there's no way I could have passed all that data through something that's like on a quantum computer, because if the fidelity is like 99.98 or 99.995, that's still way higher than classical or CPU, GPU kind of stuff. Okay, so so Mary said again, so Canadian tech companies in this space. Okay, and you know, Toronto is big too. So Toronto has a company called Xanadu with an X, and Penny Lane, which is their open source quantum machine learning platform that I use all the time, is owned by Xanadu. So Xanadu does photonics as well. Yeah, so I would say that, and Mary had mentioned here too, you know, Vancouver, it's definitely a global effort. I was on a call not too long ago, within the past like week or two, and there was a gentleman just, you know, urging for, you know, support for faster projects so they could fix things with quantum computing in Canada, right? So it was a valid concern that he had. And is funding cutting edge. And I don't have too much as far as Canada funding, Barry. And again, so feel free to come on. So Mark, you can come on again, or Reza, you can come on as well. You can either unmute or come on by video. But, you know, in the US, and a lot of this is reflected by other countries too. In the US, the government, between NIST, DOE, and NSF, $800 million every year the past couple of years. So I've done a report on that for sure. I know, like I said, like Toronto in specific, you have Vancouver as well. China's huge. UK is trying to catch up. So, and then you have Australia that's also in the game as well. Japan has, quantum sensing. They have some good papers too on quantum sense, like a rat's heart, and getting better results off this diamond quantum sensor. So more of like that full, I think they're going more towards full applications with that too. Any other questions? So I see kind of new people popped in here too. And then, so tying this back into medical is the biggest kind of the shiniest object out there is the IBM Cleveland Clinic. IBM installed the first quantum computer in healthcare. I think this is a couple or several months ago, I think March actually. And it signifies that there's, you can't just put into one of the leading healthcare systems a quantum computer and don't expect further development, right? That's my opinion on it. So what it means is basically, there's hope and confidence. The technology keeps improving, especially in computers and the methods that we're using, even in quantum simulators too. And they have a 10-year partnership between IBM and Cleveland Clinic. There's also Mount Sinai Hospital and Sandbox AQ. Now, Sandbox AQ is a Google spinoff, and they have privacy-related, projects. Cybersecurity in this case is going to be patient data. So that's that one. And Sandbox AQ recently got $500 million in funding. And the technology behind that isn't too off from what I'm using. It's these linear quantum algorithms. The difference is that they use, they're called NIST. They're standardized quantum algorithms, and they're basically doing the application of making sure companies are equipped with these, open source algorithms for cyber defense, so we don't get attacked internationally. And this all relates to, patient data for sure, because that's a huge concern that's out there as well. So any other things? Because we had a question regarding kind of like the medical and quantum bits, and feel free if you want to come back on, Reza, as far as, why switch to quantum? And you have to understand the fundamental pinnings behind it, I would say. So, like high dimensional feature space, most people don't know what that means. But if you watch enough of these YouTube videos, like MIT, Seth Lloyd and others, it makes sense, right? Like it's not just entanglement or superpositioning or interference. You're dealing with the quantum bit and the way that it interacts with data and what it can do with data. So I would say it's very promising in that regards, where most, if not many, people will be going off after bigger circuits and, the mainstream news of, more control, not gates, the better 100% time, those types of things. So it's really an academic approach to it all. So there was another thing from Mary here. So sometimes when it doesn't match the company outlook on their technology. And I mean, based on the previous kind of comment that you had there, is maybe getting more funding for Canada, it sounds like, is your inquiry to kind of progress the technology. And that's the same thing as everything struggles with. I mean, many startups struggle, with getting funding, growing in certain ways, those types of things. But I really don't have too much more on the, the Canadian tech space. The news doesn't match the company outlook. Oh, okay. So maybe you're saying that the news, Mary, is kind of overinflated or under. I don't get too much as far as like the global kind of stuff. It's mostly the US stuff.
Sorry, I just mean that like sometimes the news is they're not really focused on what I think would be like, what the technology is, or like the future for the technological improvements, like how it can open up new space for products or markets. Mostly they're concerned about like companies consolidating. So they're not, I don't think they're looking towards like the future. And the reason why I was just writing this in the chat was that I'm just looking at places and locations where there's like you know, support for this type of technology, because I'm looking to go to school, you know, maybe to study this. So I'm just looking to see where there's some kind of support for, you know, school institutions, research, and also for companies, industry.
Yeah, and I would say that you have to be aware of both ends, because like, you know, I would say I was just too overly optimistic based on just mainstream news without running applications. And now I'm a little bit more down to earth with it all. Like I can actually plan out, you know, my next projects and which, you know, simulators and all this kind of GPU stuff. But yeah, it's interesting too, because there's no 100%. So with quantum algorithms, you can't test them, right, on the quantum computers that they're designed for. So say if you have 1,000 qubit quantum algorithm, there is no 1,000 qubit quantum algorithm. So there's no 100% guarantee as far as like what people project the technology for, if things go smoothly the whole way, that your algorithm that we're just waiting for better hardware to plug in will work, right? So that's the kind of like downside to it. Now, yeah, so there's definitely a balance, right? Because you want to, as an optimist, you would say, okay, we see something's coming in called quantum computing. It runs off quantum mechanics and quantum bits and all this stuff. And we see the progression to it, but will there be, number one, like, say for instance, like a news outlet, have they got burned previously on deep learning or something like that? That's the biggest analogy I have for it, is it's the next best thing after deep learning, right? And there's a deep learning FDA approved algorithm already. So I would say that, you know, is a lot of times there's not 100% guarantee that, you know, the way that we're forecasting is, you know, and now we'll have 1,000 qubits, and that means that we'll have this exponentially better power, like you're looking at a map, but that hasn't happened yet, right? So there's no guarantee. So I think there's that on one regards, is they just don't, you know, want anything for them to put so much time and effort, and then say in 5 years, you know, it's not close to what people were expecting, because there is no guarantee, you know, it's emerging technology. And, you know, there's, if you need to convince yourself further, it's, I think the kind of the good resting point will definitely be this hybrid interplay between CPU, GPU, QPU, or even, you know, CPU, GPU, and also those two simulating, you know, quantum mechanics, those types of things. It's likely, you know, from reading so many papers, it's just like, you're not going to likely always get that max result that you're progressing, you know, based on some other chart that you've seen. You know what I mean? So there's, I think a lot of organizations, they build in safeguards, so they budget things, right? Like they budget anything. There's, if you look on YouTube, there's so much like fake quantum news where it's just like like a AI rehashing some other articles put together, that kind of stuff. But I think that's what organizations are kind of like concerned about. But at that same time, you know, the quantum simulator approach seems, it's near term. Like if I had all of my ducks in a row, I could do a very cool looking thing on paper. I still have to run it. But again, this is, you know, GPU, CPU kind of thing. And then, you know, simulating quantum mechanics. But to everybody out there, I'd say that's the biggest thing. As somebody has shared before, NISQ, is you have to keep that in mind. The amount of noise that we're in right now is relatively high compared to conventional computing approaches. And to come down off that, it's going to take some time. And I believe there'll be, you know, a useful, practical quantum computer, you know, coming up. But at that same time, if you have, you know, experiments to run, I know for sure if I do 3,500 images on a linear quantum algorithm that's part of even a bigger, you know, classical neural network, with the amount of noise that's in ion trap or gate-based superconducting qubits, it's just not going to it's not gonna go too well, right? So NSF, and I mentioned them, on this discussion, they said that we should be getting a practical quantum computer this year. So if you talk to other organizations, and there's been other ones in different discussions too, they say we don't know what that means, right? So is that 99.999%? But that's still way off of, like, that's the error rate is still really, really high. So I think the focus on quantum computers, the real hardware, is going to be which applications is it okay to use quantum computers. So at 40 qubits, a quantum computer is a lot faster than a quantum simulator, for like I think it's getting up to a supercomputer on the quantum simulator. However, the quantum computer, it takes up, and this is a Terra Quantum algorithm, 0.02% of the amount of time than the quantum simulator. So that's the thing. If you're under 30 qubits, they pretty much said just use a quantum simulator, because between the lag and the internet and the actual device firing up, that kind of stuff, that it doesn't make a ton of sense to run on a quantum computer unless it's over 30. So there's pushes though, right? Like, so developers get push. We just want to run on a real quantum computer from the best name in the country. And, that'll be the task. And, it just takes time, right? For the quantum computers kind of to catch up to simulators, especially at lower qubits. I hope that answered your question there. So there was something else hard to figure out what, and I would, Mary too. So if you want to go on YouTube, search for like a panel, quantum computing panel or quantum computing discussion. Yeah, but it'll typically give you good ones up front if you change it to the date. So say if you want like the most recent videos, then there's some sifting through, because there's some AI being generated and it's not like a real person speaking. Not as helpful, it doesn't seem like. Awesome. For institution, yeah. So, and we'll keep on healthcare for sure. So I just want to make sure I'm understanding these right. So Mary says, I'm just looking into locations where there is support and investment from government for institutions and industry in this field in regards to healthcare. So as far as the big organizations seem to be, embracing quantum, Cleveland Clinic, Mount Sinai Hospital, NYU Langone, they do the MRI analysis with quantum sensing, quantum computing with Fermilab. Those are the big three that I found. And there was, I want to say Mayo Clinic just recently, maybe even today. So the support appears to be out there. So yeah, there was a big one. If it wasn't Mayo Clinic, it was some other big one. Support for it out there. Part of it's just waiting. So if you want to get results, you're going to have to run a quantum simulator, just with the noise levels. So there's a lot of stuff that's just not published. So say, for instance, they're probably doing experiments, the quantum computer by IBM and Cleveland Clinic isn't going to just sit there. So if it's doing it on a real hardware, where it makes sense. And then, like I said, sometimes the noise isn't quite an issue, but it's front and center. You could see the thing being installed in Cleveland Clinic, like an aerial camera, like kind of live kind of thing. And, it's the same thing. I mean, the closest analogy to everything that we're talking about is deep learning. So deep learning, to run these neural networks, which is based on brains. So if you have neurons coming in and then it goes 3 to 2, those types of things, and then you're doing things between layers. The hardware for that was not available until late 1990s and until early 2000s for deep learning, right? That was a significantly harder task than doing linear algorithms. Basically, deep learning means, so if you have images, you're learning off of a training set. And then when you introduce new data, then based on those results, and they're called weights and biases, then based on that new data, it can predict what they are. And how far that prediction is off from the real values is called accuracy. So that's the crux of deep learning. So in imaging, it's called convolutional neural nets. And the first FDA approved deep learning algorithm wasn't until 2017 by a company called Arteris. And then this is cardiovascular kind of work. And then, ever since that point, up until they published October of last year, there's 521 approved algorithms. And many of the more recent ones are deep learning based. So the same thing's going to apply for quantum. So the trade-offs with deep learning is a lot of times you don't get the same result if you run it from hospital to hospital, but the results tend to be a lot better. So FDA categorizes this under probable benefit. It was greater than probable risk in order to incorporate deep learning technology. So the same thing's going to be for quantum. I mean, the quantum stuff, especially on lower systems, CPUs and GPUs, it's slow, right? But it's noise free. So if patient needs results within 6 hours, stuff like that, it's just it's very specific to the cases. Awesome. Anybody that we haven't heard from? And then, I appreciate all the comments here. And we're kind of moving along here. So any of these kind of organizations, and it sounds like, we talked about Canada a little bit, then University of Chicago, Harvard, East Coast, University of Maryland, East Coast, Terra Quantum, I think there's Switzerland, QuEra, Boston, NVIDIA, basically all over the place. I don't even know where the headquarters are. University of Southern California, Stanford, University of California, Berkeley. So we talked a little bit about and this is what this is, quantum computing leadership. John Martinis, he got his degree at UC Berkeley. He put in like 16 years at UC Santa Barbara. He was the lead for Google quantum computing for quantum supremacy. In October 2019, they published the first ever quantum computer with quantum supremacy. And he's posted on a lot of issues regarding a lot of different problems being solved with quantum computing, but all of this wouldn't be possible without these foundational leaders. And I'd mentioned Scott Aronson also had a UC Berkeley degree, Seth Lloyd, Harvard, who's now at MIT, and there's many other. I mean, Richard Feynman, the late Richard Feynman. We also have John Presko currently. I would even say one of the speakers on this discussion, Salvador Ivanegas-Dreyka, he published a book on quantum image processing, which is before you create the image. And, Salvador, who was on this discussion, he was working on quantum computing since like 2004. And you see where we are today, still trying to get universal quantum advantage. John Martinis, his first paper was the year that I was born. So this is 1983. And Scott Aronson, he published this book. I can't remember. It's a more comical book relating to quantum mechanics. He's at UT Austin right now. But yeah, a lot of this is the groundwork has been laid, for sure. To be able to run a program, I run programs all the time on Google Colab that uses a quantum simulator and other GPU for deep learning, in combination, and it just didn't come from nowhere, right? So, any other questions or comments with that? So either on the quantum side or the medical side. And I would say another one that pops up is definitely University of Waterloo. So they're funded partially by the BlackBerry or RIM, one of their co-founders, Mike Lazaridis. And then so they just put in a new quantum institute for research up there. And this is in Waterloo. And they've seen a lot of the developments, even from like the core components of making up a quantum computer, like they published like, oh, we just solved this specific thing. So it's definitely, what they say, on the shoulders of giants. So anything else? And, if not, so I'll give you a sec as far as like, you can put it in the chat or you can unmute and then come on. But I think the one that sticks out the most is, as far as really pushing the needle, might be the NVIDIA. So basically you can install these packages, pip install, these types of things if you're a programmer. And the QuAntum in specific, they break it into two things. So, and this is going to get somewhat technical. So you have state vector circuits. So, okay, so these are typical quantum circuits or algorithms that you see all across the internet, but they're limited by RAM. Okay, so this could be GPU RAM or CPU RAM. But they can do entanglement, and they can do, basically deeper networks. Okay, so that's the thing most people are using. They're called state vector quantum simulators. And the second thing that NVIDIA puts up is basically, instead of doing state vector, they're calling it tensor network. So you have 2 times n the amount of RAM required, where n is, I think, the number of gates. So you can go out hundreds or thousands of qubits with this, but you can't do much entanglement, and you're pretty much limited to single quantum gates. Okay, so that falls under the whole notion of tensor networks. And there's likely going to be hybridness between the two. And even if you're restricted by time with state vector, if you have multiple GPUs in quantum simulators, which typically run slower, then I believe that's cutting down the time drastically. And I want to say they published something above 1,000 qubits that they did, which most people don't think quantum simulators can do. And so it'll be interesting because, again, it's limited. It can't do deep neural nets as much. So it's mostly shallow circuits, and you can convert a state vector circuit into that. And then now you have the opportunity to access thousands of qubits. So I just signed up and, I just got to go through it. Typically, the hardest part is getting your pre-existing program to work, with some of this other stuff, right? The installs and what have you. But it's an amazing field, because the more, and I switched to just application as of a couple months ago, and the more you get into quantum, it's like, you read this paper and it's like, whoa, well, this cuts down on this significantly, and running like a 20 qubit circuit is going to be like nothing, probably even in a year from now on a simulator. Now, when I talk about all this, I'm talking about other big data that you're working with. So if you have like thousands of other images, so if you can cut down on all that stuff, or even classes, with the types of classes of images, then you give it more room. It's not going to consume a lot of the RAM, basically. So random access memory, either GPUs or CPUs. So that was that. And then, as far as where it's all going, I don't quite know the regulatory process for quantum simulators in medical. And then definitely the other stuff as far as quantum computers, maybe the ion trap coming in first. It kind of has a lead right now on connectivity and not as much noise, but it's still relatively noisy, like compared to classical hardware. So it might be some time for that. So if you're running after quantum hardware companies, just keep that in mind as far as what results you can get today. Awesome. Any other questions or comments here? So, I would just say, like, the government, so quantum computing is a government initiative. So early 1980s. And this is NSF started to fund the technology. And then ever since then, it's gone into, definitely universities. And there's certain universities like MIT in specific is on fire for quantum. They have the thing called Torch Quantum, which is based on PyTorch. And it's basically allowing you to, code in quantum. And I think it's a lot closer to PyTorch than say, if you have like TensorFlow compared to, TensorFlow is to TensorFlow Quantum, and I think Torch Quantum is a lot closer to PyTorch. So those are the quantum and classical analogs that I just mentioned. But people ask me like, what in specific should I code with? You know, should I do TensorFlow Quantum, or should I do PyTorch, or should I do Torch Quantum or Qiskit or PennyLane? And it just depends. Like, are you building a new model? What was your previous favorite conventional? Was it PyTorch or TensorFlow? You know, and I think you'll have the least amount of struggle kind of sticking where you're currently at if you're a programmer. Awesome. Any other last questions or comments here? Thank everybody for coming on. And, you know, just keep in mind, so things are always improving too. There could be a breakthrough in hardware, but the trend, I got seriously into this, say October, well, a little bit before September of 2021, right? And I was interested in it the previous year, but, you know, fully dedicated to it. And it has been, it's a steady progress through a lot of this. Even if there's a Nature paper claiming quantum supremacy, you know, how are you going to use that to improve your application today? Because they might not even have the computer available for rental, which now I think they do. So the Xanadu has Borealis up on AWS Briquette. So it's available. It's photonics based, which is room temperature, but it may have other things that it's trying to work through there. Awesome. And then if not, so we covered, you know, basically 9 organizations here, and don't give up on your quantum journey, keep going. And especially, I think, Mary, it sounds like you're onto something there. Definitely keep going with it. And I wouldn't rely solely on just mainstream news. I don't even watch a ton of mainstream news, but it's more about the overall state of the industry. And I've kind of rehashed that a couple times in this discussion. And if you're into something, definitely go for papers, you know, read a lot of the Google Scholar papers, or even Nature, those types of things. Other than that, I mean, if for applications too, if you want to get closer to an application, start with a model that's already previously built, optimize parameters, change data sets, those types of things. It's called PennyLane. So it's Xanadu PennyLane. So just PennyLane, just like from the Beatles song. And then, so you can use PennyLane for that, or you can go through some of the IBM Qiskits. I was able to perfect one of the Qiskits to 100% training, and I think it was testing accuracies. So I basically did that, but you do that. And then, say for instance, next models, incorporate your data set, read some more papers, make things better too. Awesome. Yeah, and definitely I'd be interested to hear about this, because it's interesting, right? The Canada stuff. I know the Calgary, they claim that it's the quantum city or city of quantum in specific. And then, so between maybe those 4 cities, Vancouver, Waterloo, Calgary, and Toronto, that's definitely, you know, they're definitely into it. And Calgary, they have, I believe, because this is quantum based. They were in a hospital presenting something that, you know, basically, I think the healthcare system in Calgary supports quantum as well. Awesome. Okay, I appreciate everybody coming on. So this has been discussion 85, June 1st, 2023. Keep strong in your quantum journey. Have a good night and have a productive rest of your week. Take care.